right, hey guys, we're going to be doing the Chapter 6 worksheet. In Monday, Wednesday, and Thursday's review sessions this week, I did get through the first 2 pages of Chapter 6, so I'm going to go ahead and skip to the 3rd page of Chapter 6. If you guys have any questions about the first 2, let me know at the exam review, but we're going to skip to the 3rd page for time's sake, okay? So the first reaction we need to go over is halogenation, which I got to in a couple of my SI sessions this week. Hold on 1 second. Okay, so halogenation. So halogenation is the addition of X2, so Br2 or Cl2 or something like that. And remember, we have those 3 important questions that we're going to ask ourselves. What are we adding, where are we adding it, and how are we adding it? Okay, so the answer to what are we adding is 2 X's, so 2 halogens. So like Br and Br, something like that. For this reaction, where we add it doesn't matter. And the reason is because, first of all, you're adding 2 of the same thing, so it's not like you add the hydrogen to the less substituted carbon. You're adding 2 chlorines or 2 bromines, so you really can't distinguish which one you added to which. And also, this goes through a bridged intermediate, so actually what happens is that the first thing that adds kind of binds to both of the carbons involved in the alkene. So I'll show you that in a minute. And so the main reason for it not mattering is because it's bridged. You always want to think about your reactions and think about what kind of intermediates they went through. The ones we did on the first page, hydrogen halide addition and acid catalyzed hydration, both go through carbocation intermediates, and that tells you specific things. Knowing that this goes through a bridged intermediate should tell you other things, so we'll go through what it tells you. One of the main things it tells you is that it's going to add anti. Okay, so anti-stereoselective, that's how we add it. And just remember, anti means that you added the 2 substituents that you add to across the double bond, you added them from opposite faces. And that's always going to be true for a bridged intermediate. Okay, so what drives this reaction? Let's say you have Br2. We don't see a distinct delta positive or delta minus like we do with like HCl or something like that. But what really drives this reaction are these instantaneous dipoles that you learned about in Gen Chem and a little bit this year too. So basically at any given moment, these electron shells could be distorted to the point where you would get this delta plus here and a delta minus here or something like that. Okay, so that's really what's going to drive this reaction, the fact that there are these instantaneous dipoles, and at any given point in time, one of these bromines can have a slight positive charge on it. So let's see what this reaction looks like. Okay. So what's going to happen in this reaction is at any given moment you'll have a delta plus here and a delta minus or something like that. So this electron-rich area is going to be your nucleophile as it was in the other reactions, and it's going to attack the area of low electron density. So high electron density attacks low electron density. Okay, but how a lot of professors draw it, it kind of just depends on who your professor is you break this bond, but this chlorine wants to basically take its electrons and attack this carbon, which is more electropositive because this carbon has more electron donation. It has electron donation from this extra substituent, whereas this carbon only has this. So if you were to break this bond, basically you would get, we don't end up getting a carbocation. What we end up happening is that this chlorine comes back and bonds to this carbon as well. So this is called a bridged intermediate, and this is what it ends up looking like. Okay, so I'm going to say this came in from the front face. So if this came in from the front face, I'm going to draw these chlorines both on wedges. They have to be in the same plane. So since the chlorine is only one atom, it cannot be in 2 planes of space at the same time. So this has to be coming from the front from both sides. So that means this methyl would have had to go back. Okay? So now, what else do we end up with? We end up with a positive charge here. Okay? And since this carbon is more, since this carbon has more of a delta positive on it, since it has less electron donation, this chlorine is really, it's bonded to both, but it's unevenly bonded. So what happens is this chlorine starts to come closer to this carbon, and less of the bond is involved with this carbon, more is involved with this. So what that leads to is a delta positive here, okay? So you get this delta positive, and that's where your chlorine that you have in solution, which is negative, is going to attack. So basically what I want you to remember from that is that your chlorine that attacks is going to attack the more substituted carbon. Okay, so attack the more substituted carbon. And if this were to attack, it couldn't come from the front face because that's where this chlorine is. So it had to have come from the back side. So if it came from the back side, then it would be pushing things forward. So this is also in the back, so it has to move this methyl forward and subsequently breaks this bond here to the chlorine. So what you end up getting is this chlorine coming from behind, pushing this methyl group forward. So you see the methyl was on a wedge, or on a dash, now it's on a wedge. The chlorine comes from behind, so it's on a dash. And then this chlorine, this bond just breaks as this pushes forward into that plane of space. So this chlorine stays attached to that carbon. All right? So one thing that you should think about for this is that this chlorine didn't have to come in from the front. It could have actually come in from the other side, and then everything would have been reversed. So what you would get is something that looks like this. So if this chlorine came in from the back, the first chlorine, here, then the second chlorine would have attacked from the front. So that chlorine would end up on a wedge, this one would end up on a dash. Notice that these end up anti, okay? And like we said before, this reaction is always going to be anti-stereoselective, and that's always true when you have a bridged intermediate. Now, what am I missing? I'm missing this here. This substituent is not affected by the reaction at all, so its stereochemistry does not change. And what's important about that is that all of the stereochemistries for these group change, but these do not. So really what that means is that you end up with diastereomers, okay? So typically if this substituent hadn't been there or hadn't had stereochemistry, these would be enantiomers because the chlorines could have come from either face with equal probability. But since you have this and you have one stereocenter that did not reverse, whereas the rest did, the relationship between these two is that they're diastereomers. All right. So that's pretty much it for halogenation. We're going to move on to hydrohalogenation now. Okay, so hydrohalogenation is when you add like an X2, but you also add H2O. So Br2 and H2O or something like that. So the three questions that we ask, what, where, and how. The first question is going to be what. So what do we add when we do hydrohalogenation? Kind of as the name suggests, you're going to be adding a halogen, and you're going to be adding an OH group. Okay? Where this adds, this is going to add Markovnikov. So you might be thinking about what that really means, because if you remember when we talked about Markovnikov before, the hydrogen went to the carbon that was less substituted, or the hydrogen went to the one that had more hydrogens, but we're not actually adding any hydrogens. We're adding a hydroxyl and an X. So which one adds to the less substituted carbon? That's going to be your X. So your halogen is going to, basically you can think about your halogen as your hydrogen and the other reactions. So this adds to the less substituted carbon. This adds to the more substituted carbon. The third question is where, and this adds anti. And this reaction is very, very similar to the last reaction that we just did. So it also goes through a bridged intermediate. Okay, so let's go ahead and look at this. Okay, so we're going to draw a line to this chlorine and a line back so we know that we're forming the bridge. And we're going to break this bond, sorry. Okay, this Cl also has a plus charge on it because it has 2 bonds to it. So the next thing that we're going to add is going to be water. Okay, so now where does the water add? Remember how I said before that the carbon that's less substituted is going to basically be taking more of the electron density from this chlorine bond than this carbon would be taking. So that basically frees up the ability for this water to attack the more substituted carbon, just like the Cl- attacked the more substituted carbon in the last example. So this OH2 is going to attack this carbon, and it's going to break this bond. Remember, it has to attack from the opposite side of the Cl, so it had to have come from the back side, which means we'll get an OH2 group on the back side. It would have pushed this methyl group forward, so we'll get a methyl coming forward. And this Cl would have stayed the same. Okay. So that's the whole, that's almost the whole mechanism, sorry. So the next step is going to be, we have an OH2 plus. So basically the rule for orgo is if you don't know what to do, you should just add water. So, and that's not really a great rule, but I've heard professors tell me that before. So basically, we have this OH2 plus group. So if we have more water in the reaction. So if we just attack a hydrogen and break this bond, then we'll get a neutral molecule, which is always going to be better to end up with. All right, so that's what we end up with. Now, the chlorine in the beginning could have come in from the backside. And if it had, then everything here would be reversed because the OH2 would have come in from the front. So what you would get here would be this. And the relationship between those two is that they're racemic. So these are enantiomers. So this is going to be a racemic mixture of these two. So you get 50-50. And basically on exams, if you have like predict the product or something, you can typically just write one and then write racemic. You don't have to write both of them out. For diastereomers, it might be different. You should just ask your professor or listen to what they say in class. All right. We're going to do one more for that example, or for this mechanism. Okay, so we have this, and we're reacting it with Br2 and H2O. So what do we end up getting? So what we end up getting is this alkene is going to attack the bromine, which is also going to come back and attack it. And we're going to break the bromine off. So what do we get now? So we have this bromine. I'm going to draw the bridge a little bit differently this time. I'm going to draw the bridge in the plane of the paper. Okay. So this is the bond, the alkene that we just broke. And then basically I'm going to draw everything that was going up on the alkene going back. And then this coming forward. So what you can kind of think of what I just did is this Br came on top of it essentially, and I just turned the molecule so that the Br was in the plane of the paper. Hopefully that makes sense. Okay, so that also has a positive charge on it. Oh, I'm going to make this a little bit different. I'm going to make this CH3OH. So that's called methanol. All right, so it doesn't have to be H2O, but you have to have an OH group that you can add. Okay, so if you had methanol, then the next thing you would do is take this CH3OH, and you would use the electrons that are on the oxygen to attack the more substituted carbon. Okay, so remember, the first thing that adds goes to the less substituted carbon because it's Markovnikov. So this goes to the more substituted carbon, and you can break this bond. Okay, and I'm going to keep this in the plane of the paper, so let's see. All right, so if this was in the plane of the paper, then basically that had to have come from the other side of the plane of the paper, so the bottom part, right? So this was on top, this had to come from the bottom. You also get a plus on this. Okay, so the next thing that you do is just add more of your reagent, so more of the CH3OH. And this time you can use the electrons to deprotonate. Okay, so you end up with an OCH3 group. So it's not necessarily always going to be an OH. It can also be an OR, whatever that R group might be. Okay, so just important things to remember from this reaction. This is adding anti, so they add to opposite sides of where the double bond used to be. Okay, so this is adding anti. In the last example that we did, it did add anti as well. And it goes through a bridged intermediate. All right, that's it for hydrohalogenation. We're going to move on to oxymercuration reduction. Okay, oxymercuration reduction. For this one, your reactants are not going to be as intuitive as they were for the other ones. You're probably going to have to memorize these reactants, or these reagents. Okay, so we use HgOAC2 and H2O and NABH4 as our reducing agent. This is called oxymercuration. So this is mercury, so your oxymerc, and then reduction by NABH4. All right, so what are we adding across the double bond in this? This one, it's not as obvious what we might be adding. What we're actually adding is water. So what that means is that this is one of the 3 ways in this chapter that we're learning how to add water across the double bond. This is the second way. We already learned acid catalyzed hydration, and we're going to learn another one in a minute. All right, so what are we adding is water. Where are we adding it? We're adding it Markovnikov. And if you guys remember, with water, if you add something Markovnikov, that means the hydrogen's going to the less substituted carbon, or the OH group is going to the more substituted carbon. And then how are we adding it? We're adding it anti only. All right. This reaction also goes through a bridged intermediate, so you want to keep that in mind. So you're learning 3 bridged intermediates. You learn 2 carbocations, 3 bridged, and we're going to learn some concerted in a minute. So for this reaction, just so you know, basically, this is HgOAC2, and when you put it in solution, what you end up getting is HgOAC plus and OAC minus, okay? All right, so what we're going to use actually to react is going to be this here.
The Teaching Center. UF's Learning Resource Center.
All right, one important thing to mention for all professors, as far as I'm concerned, is that you have to write 1 and 2 for these reactions. So for like hydrohalogenation, you just write Cl2 and H2O or something like that. But for these reactions, if you were to put these two in together without writing them, without doing them in completely separate steps, you would not get the reaction that you're looking for. So it's really important that you write that they're separate steps. I'm sure all your professors will emphasize that. All right, so in the first step, we're adding HgOAC2 and H2O. Okay, so what this really reacts with is the HgOAC plus, okay? So what's going to happen here is that this is a plus. So if you remember, and this is a bridged intermediate, so if you remember from like the Cl2 and stuff like that, basically what we were doing was we were attacking the positive center, but then the electrons were coming back and attacking the carbons as well. So it's the same thing that's happening here. This attacks, but then this comes back and attacks it. And then it actually stays bonded to the OAC. So what we get is this. Okay, but just like everything else that we've done with bridged intermediates, you end up with a positive here. Okay? So the next thing we're going to do is we have water in this step as well. So we're going to use the water, and we're going to attack the more substituted carbon. Okay? So the water is going to end up being our OH addition. And our OH needs to go to the more substituted carbon. So we're going to do the same thing that we pretty much did for the last mechanism. Have the water attack the more substituted carbon, break this bond. So if this was in front, this water had to have come from the back. So the water is now back here. The methyl group is now coming forward. And the HgOAC is also coming forward. All right. So the next thing we want to do, same as the last reaction, is deprotonate. So we're going to deprotonate this by adding more water, attacking the hydrogen, breaking that bond. Okay, so that's what we end up with here. So that's the end of step 1. What you can see from step 1 is that the two things that we added so far, what we've added is HgOAC and OH. And they've added anti, right? So they've added anti, that part has already happened. And they've added Markovnikov in a sense, because what's really going to happen is that hydrogen is going to replace this HgOAC2 in the reduction step. You don't have to know the mechanism for the reduction step. If any of your professors tell you that you do have to know it, let me know, and I'll go through it with you. But for now, I'm just going to tell you guys that step 2, which is adding NaBH4, is basically going to keep the stereochemistry the same, but replace this H with replace this HgOAC2 with a hydrogen. All right, so that's what you end up with. Now, my question is this racemic? So take a minute to think about that. Pause the video if you need to, because that's a really important question. Is this a racemic mixture? Could it have happened the other way? So the answer to that is going to be no for this one in particular, because this hydrogen doesn't have to be shown because it's a hydrogen. Before we were adding like Cl and Cl, but if you just erase this hydrogen, like you typically wouldn't see it, right? This center right here, which looks like a chiral center, is actually not chiral because you have an OH and a methyl, but then you have these groups which are the same. So this actually isn't racemic. This is going to be your only major product. So you want to be hesitant to write racemic down for everything, especially for the bridges and stuff. You just want to make sure that you even have a chiral center, because something can't be racemic if it's not chiral in the first place. Okay? All right, hydrogenation, oxidation. So this is our last way of forming water, or adding water across a double bond. So for hydrogenation oxidation, your reagents are going to be BH3 complex to THF, and then H2O2, OH minus, and H2O. All right. So now our questions for this are what, where, and how. What are we adding? Like I said, this is our third method of hydration of an alkene. So we're adding H and OH. Okay. Where are we adding it? This one adds anti-Markovnikov. So that's how this is different from the last one. It adds anti-Markovnikov rather than Markovnikov. And it's also different in terms of how we add it. This one adds syn. So this is a syn addition. This is the first syn addition that we've seen so far. So the ones that add anti are typically bridged intermediates. The ones that add syn are typically concerted intermediates. So now we're being introduced to our third form of intermediates. We have carbocations, we have bridged, and we have concerted now. So what does concerted mean? Concerted means that both of the substituents add on at the same time, and they're connected to each other. So you can't take the molecule and move it into two different places in space. So they have to add on to the same side at the same time. So I'll show you what that means right now. So what you're adding is essentially this BH3. So the way you want to think about the BH3 is as H attached to BH2. Okay? So you can think about water like that. Sometimes you like H attached to OH. So this is H attached to BH2. And the way this concerted mechanism works is that this hydrogen, basically, you get addition to this alkene at the same time. Oops, sorry guys. So what you get is this like square looking thing, and the hydrogen, which is attached to the BH3, or the BH2, to make BH3, they both add at the same time. So now why does the hydrogen add up here rather than down here? That has to do with sterics. So what happens in this reaction is that the hydrogen adds here to the less substituted carbon. So if you can think ahead, we know we're going to end up adding H and OH. This is the H that we add. The BH2 will eventually be replaced with OH. So since the H adds to the more substituted carbon, that makes this anti-Markovnikov. Hopefully that makes sense to you guys. So since the H adds to the less substituted or the more substituted carbon, you get the H here and the BH2 here. And essentially what you get is this concerted block. It's often drawn like this. So like partial bonds between all of these. And then what happens is you often don't have to know this mechanism. You guys can, again, let me know if you need to know this one. But basically what happens is this BH2 then does the same thing with another one of these reagents. and you end up with Br2. And by R, I mean all of this. So you end up with this large structure on the Br2. So that's why you can't add the B to the more substituted carbon. It's because of sterics. So after 3 times of doing this, you end up with Br2. Again, any R is just this whole group attached to it. Okay? And so you get this concerted step, so it ends up being syn because they added to the same side. And then eventually you break this bond between the hydrogen and the Br2, and the Br2 gets replaced by OH. All right, so what did I end up showing here? I didn't show the mechanism because, again, I don't think you need to know it. It's very complicated. You guys can ask your professors if you do need to know it, and if you do, then I will definitely go over it with you. But basically, the Br2 gets replaced by OH, and so you end up getting water added across the double bond. What's most important about this is that it adds syn, so they add at the same time, so these H and OH end up having to be in the same on the same face. All right. All right, so the next one is going to be syn hydroxylation. So we're done with the main reactions for this chapter. The rest of these you typically do not need to know the mechanisms for. It's kind of just like, everyone says not to memorize for orgo, and I don't suggest that you do, but these are more of like just knowing what happens in the reaction, not necessarily knowing the full mechanism, because they're a little bit past the scope of this class. So for this reaction, you have OSO4, and the second step is going to be NaHSO3 and H2O. So syn hydroxylation. So what's hydroxylation? Hydroxylation is adding OH minuses. So if you have syn, you add, the name of this reaction gives away some of our answers to these questions. So what we're adding is 2 OHs. So add an OH and an OH. Where are we adding it? Doesn't matter because they're the same substituents, so you can't say that one added to the less substituted and one added to more. And then how are we adding it is going to be syn only. All right, so what you end up getting here is OHs added to both sides of the double bond with a syn addition. So this goes through a concerted mechanism. Basically, let me go ahead and show you what happens, at least in the first step. So OSO4 looks like this. After the first step is done, this is what you end up getting. Okay, so the alkene attacks the OSO4, and then you break, you basically attack both sides of the O's, right? So you get this. So that's why it has to be syn. It's because these are all attached together. So you can't distort the molecule to have one O add in the front and one O add in the back, right? So basically these are going to add syn, and then this whole thing gets replaced by H's. So that's in the next step with NaHSO3. And then we get to this eventually. Now, is this racemic? Could it have added from the back for both? It could have, but for this one in particular, this is a meso compound. So you want to be careful with saying that, with saying racemic for anything. All right, so that's it for that one. We're going to do catalytic hydrogenation. Hydrogenation is adding hydrogens across the double bond, which is also called reduction. So if you're adding hydrogens, you're reducing. Typically, if you're oxidizing, you're adding oxygen or something like that. All right. So catalytic hydrogenation, basically your reactants are going to be H2 and one of these, PT, PD, or CD. So platinum, palladium, and cadmium, I think. All right. So the three questions are going to be what, where, and how. So what are we adding? For this reaction, we're just adding H's. These act as catalysts. They act as, basically they act as catalysts in the reaction, but they're not used up in the reaction. So we get them back in the end. So where are we adding this? Doesn't matter, right? Because they're the same thing. And how? This is always going to be syn. So syn hydroxylation, syn hydrogenation. So just remember all that. So sometimes you'll see PT with like a circle or PD with a circle. That just means the metal catalyst, basically. It's in its metal state. All right. So this is going to be syn hydroxylation, or syn hydrogenation. So basically, at the end, what you get is an H here and an H here. So you've reduced this double bond to just having hydrogens, okay? That's pretty much all you need to know for that reaction, is that they add syn, and then you add two H's. All right, and so the last reaction of Chapter 6 is called ozonolysis. I think it's the coolest reaction of Chapter 6. All right, so what do you need for ozonolysis? The first step is going to be O3. And the second step is going to be CH3, SCH3, or CH32S. You'll see a lot. All right, so what happens in this reaction is it's an oxidative cleavage. So you're basically going to cleave where the double bond was and then oxidize it. And like I said before, oxidizing means you're adding oxygens to it, OH groups, or like turning it into a ketone or an aldehyde. So I'll show you what happens here. All right, and our questions don't really apply for this one. I'll show you why. Okay, so basically what you have, if we start out with this and we add O3, what O3 looks like, it's basically like this. Okay, so you have a positive here and a minus here. Okay. So this is going to attack this, but this is going to come back and attack this. Okay, so what you get is, I'm going to do this all in the plane of the paper, so I'm going to make these, I'm going to show stereochemistry for these. So the things that were down, I'm going to put coming out. So that's the ethyl group. Then you have the methyl group. Oops, sorry. Okay, so then you get this like five-membered ring kind of looking thing. And what happens here is, this is where the alkene was. And what happens in this reaction is that we end up cleaving the alkene. So you break this bond, just like that, and then you also break this bond. All right? So when that happens, basically what you get is, from this side of it, you basically just get this carbon attached to this carbon and this oxygen. Okay? So we make a double bond by breaking this here. So you have a carbon that's attached to this carbon, which is double bonded to this oxygen. Typically you write the H because it's an aldehyde. So you end up with one aldehyde. What else did we end up with? We also ended up with Okay, so we also ended up with this. So when we broke this bond, we took some of the electrons away from this carbon. So we end up with a positive on this carbon, still attached to the ethyl and the methyl. It's also still, we never broke this bond yet. It's also still attached to these oxygens. Okay, so we have this plus and minus here. And then the last thing that happens here is kind of strange. This is why a lot of professors don't require that you know these reactions, because they're very kind of intense. So what happens here, let's see if I can draw it correctly. I'm going to rewrite this down here. All right, so what happens here is this negative, if you drew a dipole, you would draw this dipole going up, right? So this carbon has a delta positive on it. So the negative attacks this carbon, okay? And then the electrons on here attack this carbon. Okay? So what you end up getting is, and bear with me, hopefully this will make sense. Okay, so let's see if we can count that out. So basically we have this carbon that's attached to this carbon. So this is this one here. We have this carbon attached to this carbon. And then this ends up being attached to this, this ends up being this oxygen here attached to this carbon, which is attached to these two things, which is also attached to this and this, right? Which is now attached to this. So hopefully you followed that. Let me see if I can do it again. So what you end up getting is this carbon here attached to this carbon. This carbon is also attached to this oxygen, right? This oxygen attacked this carbon here, which is attached to these two things. This carbon is also attached to this oxygen and this oxygen, which attacked this oxygen. So hopefully that makes sense for you guys. And then the last thing that happens, they don't even go through, even the professors that go through the mechanism typically don't go through this part. But what you end up with is this plus that. So that's the complicated way to think about ozonolysis. I'm going to show you basically what you need to know for ozonolysis now after I've shown you the reaction. So what you need to know for ozonolysis is that it cleaves the double bond. And then hold on one second. Okay, so basically what happens is that it's going to cleave this double bond and then it's going to oxidize it. So the way I like to think about it is that you've just cut this bond and then you kind of separate them and then you just add oxygens on. And it's that simple for ozonolysis. So this is going to be an aldehyde product and a ketone product. And you'll always get some kind of mixture of aldehydes and ketones as your products, depending on how substituted these alkenes are. All right, so that's pretty much it. Let's do one more example of ozonolysis, and then we'll be done. Okay, so what happens in ozonolysis again is that we're going to cleave this bond, we're going to push them apart a little bit, and we're going to oxidize them. So let's go ahead and draw that. Okay, so imagine that we've just like broken this bond. We're going to throw an oxygen on here and on here. Okay? So that's as simple as it gets, basically. The only other thing that you need to know about this is that sometimes they'll give you this, and they'll ask you what the original reactant was. And that's the only time this can get difficult, because if they give you something that's in a ring structure originally, then basically what it will look like at the end would be something like this. All right, so basically it would look like this, and so how would you be able to tell that what this came from? Basically, you would just realize that you have two oxygens, and since they're not two separate products like they were before, because remember, before we got an aldehyde and a ketone, now we have like one molecule with a ketone and an aldehyde as part of it. So the double bond had to have been here between these two. So basically, you would just count the number of carbons would be my suggestion. So count from this first one, 1, 2, 3, 4, 5, 6. So you know you have a 6-membered carbon ring. So if you want, you can just write it like this, 1, 2, 3, 4, 5, 6. So my first instinct would be to draw the 6-membered carbon ring. I would throw on the alkene wherever I wanted to, basically, and then I would say, okay, this is my carbon 1, right? So what has to have happened is that this would be carbon 1. You have to number them to make sure that you get them right. So here we have carbon 1 and carbon 6, and that's where they came together, right? So since they came together here, on carbon 1 we also have this group attached. And that's how you would come up with the original structure given this, or given something that looked like this. So just remember, if you get two products or more, then they came from an alkene that wasn't in a ring. And if you get something that's all in one, then it had to pretty much have come from a ring, because when you cleave that bond, and for them to still be attached, it had to be in a ring structure. All right, I hope that makes sense. That's it for chapter 6, and I'll see you at the exam review. Thanks.